Welcome to lesson number 7. Today we're going to be looking at transformations of trig functions. And today we're going to be using the knowledge gained from a transformation unit. And so when we were looking at quadratic functions and all those other types of functions to describe how the graph given will compare to the graph of y equals sine x, where x is in degrees. So if I have 2 sine x, what this is doing is it is mapping my y values to 1/2 y if I were to bring this 2 to the other side. And what this will do, this will result in a vertical stretch by a factor of 2, and this is about the x-axis. And I would encourage you to check these out on a graph. So either go to Desmos or your graphing calculator and plug these equations into your graph to really see what's going on. With this one here, my x has been replaced by 2x. When I replace x with 2x, this results in a horizontal stretch by a factor of 1/2, and this is about the y-axis. So again, check this out in your graph. What you'll notice is that your graph of y equals sine x is going to be squished in towards the y-axis. When I have something like this, y to 3y, I also have y going to negative y. So there's two things happening here. There's going to be a vertical stretch by a factor of 3, and this is about the x-axis. But I also have a reflection, and this reflection is occurring in the x-axis. So all my y values that are positive are going to go to negative y values. With this y is equal to sine negative 3 of x. My x values are getting mapped to 3x, but they're also getting mapped to negative x. So again, two things happening. There's a horizontal stretch by a factor of 1/3, and this is about the y-axis. But I also have my reflection in the y-axis. So all my positive x values get mapped to negative y values, or sorry, negative x values, and all my positive x values get mapped to negative x values. So in which of the above examples is there a change in amplitude compared to the graph of y? Well, especially if you've graphed these, 1 and 3 will have a change in the amplitude. And that's because they were stretched vertically. And the examples where there's a change in the period are, of course, 2 and 4. And this is especially apparent, again, if you graph it. So I really recommend you go ahead and graph each of these, and you'll see how the period changes and how the amplitude changes as well. Now we want to complete this table here, and if necessary, we want to use a graphing calculator. However, what we're going to find, so with y sine x, we have an amplitude of 1 and a period of 360 degrees. And what we're going to be finding is, well, we'll see how this, what happens, the relationship between my a value and the amplitude. So amplitude here is equal to 2, and it still has a period of 360 degrees. The amplitude for y sine 2 of x is 1, and it has a period of 180 degrees. The amplitude of y is equal to negative 3 sine x. This has a period of 3 and a period of 360 degrees. Y equals sine negative 3 of x has a period of 1 and an amplitude of 1 and a period of 120 degrees. So let's pause here and think about this relationship. So we're looking at the graphs y is equal to a sine b of x minus c plus d. And what happens is, if I have an amplitude of a, that is related to, if I have, an a value of A, that's related to the amplitude. So when A is 1, like it is in this first example, sine x, the amplitude is 1. When A is 2, the amplitude is 2. When A is 3, the amplitude is 3. And then for the period, we know that for sine x, for one full rotation, would be 360 degrees. And if our b value is 2, just like what we were doing when we were looking at the b value in lesson 6, we can plug it into our formula, and 360 divided by our b value of 2 would be 180 degrees. So when I have this example, y is equal to 5 sine, then this is going to be an amplitude of 5, and my b value here is 4. This would result in 360 divided by 4 is 90 degrees. With 1/3, this is my amplitude, is 1/3. My b value, 1/2, is going to be 720 degrees, because if I divide 360 degrees by 0.5, then that will result in 720 degrees. So the amplitude then is A, and the period would be 360 divided by B. So the effect of the parameter A, changing this will affect the amplitude. And changing the parameter B, this will affect the period. And in fact, the relationship between period and B is this: period is equal to 360 degrees over B. 360 degrees, of course, if we're measuring that in degrees. And for cosine, we would expect it to follow the same effect. Now, we're going to be using these formulas here in this lesson, where the period is equal to the 360 degrees divided by B, the B value. Amplitude is represented by A, but is a positive value. And if we're thinking about radians, then 2 pi divided by B is our radian measure for the period. And we'll be using these two formulas specifically for the next lesson, but if it's a tan function, then it changes to 180 degrees and pi rather than 2 pi. So here we have class example number 2, where we want to consider the graph of 4 cosine 2 of x, and we have the restrictions on our domain where x has to be between 0 and 2 pi. So first of all, we want to state the amplitude. Now the amplitude is given to us there, so amplitude, which is equal to our a value, is equal to 4 units. And the period of a cosine function is going to be equal to 2 pi divided by our b value, which is 2. And so we would have pi rads here, pi radians, if we go 2 pi divided by 2. Now we want to sketch the graph on the grid. So with cosine functions, they have a y-intercept, and our y-intercept is at 0. And since it has an amplitude of 4, we're starting it up at 4 instead of down at 1. And we know that it has a period of pi radians, so the next time it's going to be up here is going to be at pi. And in between this point and this point, it will have a minimum point at 1/2 pi. The next time it's going to be up here at pi is going to be over at 2 pi. And then we'll have 3 pi over 2 right here. And so our graph is going to look something like this. And as I continue graphing, because we're only looking between 0 and 2 pi, those are the only values that we're going to be plotting on my function. In class example number 3, we want to write the equation of a sine function having an amplitude of 2/3 and a period of pi over 6. So first of all, the a value here is 2/3. And the b value is something we're looking for, but the b value is equal to 2 pi divided by period. And so if we want to solve for b, then 2 pi divided by, or times 6 over pi would result in 12 radians. And so if we plug this in for my b value, y is equal to 2/3 sine 12x. Now we want to list the cosine function having an amplitude of 3. So a value is equal to 3, and my period is 720. So this would be 360 degrees divided by the period. 720 would be 1/2. So y is equal to 3 cosine 1/2 x. And last, we want to write a tangent function having a period of pi over 2. And so the b value here is going to be pi instead, divided by pi over 2, which is equal to pi times 2 over pi, which is just equal to 2. And my tan function here would be y is equal to tan 2x. My last example is class example number 4, and we want to state the amplitude and period of the graph. And first of all, the amplitude is going to be equal to the measurement from here to here, or from here to here, which would be 3 units. And the period of this graph, if I start here, the next time I'm going to be over here is at this point. Now, if I know that from this point to this point is pi over 2, then from here to here will also be pi over 2 units. And so if I were to combine pi halves and pi halves, that's going to result in a full pi, or pi radians. And now I want to determine the equation of the sine function, which this graph represents. And so if a is equal to 3 units, my amplitude is 3 units, and my period is pi radians, then all I need to do is find the b value here. My b value is equal to 2 pi over period, which is pi, which is equal to 2. And so if I include my a and b value, then my cosine function here, my sine function here is going to be y is equal to 3 sine 2x.